welcome to my channel. Today's episode is going to set you up to how you can find exoplanets just like Earth and how JWST is going to help us. Let's get started with this episode. But first, an introduction to the James Webb Space Telescope. As you can see from its name, it's a space telescope, which means it's a telescope sent in space to look at objects that are farther away in space that cannot be seen from the Earth. Essentially things that are not in our cosmic backyard. That being said, the James Webb Space Telescope program is still an interesting program in terms of what it can achieve, because the James Webb Space Telescope is intended to look at things that are thousands of light years away. It makes for a really interesting combination of circumstances. The James Webb Space Telescope is the most powerful piece of space technology that humans have ever produced, which will only be superseded by the space launching system once it gets ready for Artemis's first mission. And this is, of course, the most powerful space telescope to be ever built, superseding the Hubble Space Telescope by millions of orders of magnitude. I'm sure I'm saying something wrong, but please ignore it. Anyways, let's talk about the James Webb Space Telescope. The James Webb Space Telescope was launched on the 25th of December 2021. Its purpose has been clearly defined by now, and I'm sure you know a little bit about it from the news. Speaking of the news, it released a few images. The first images were released a few days ago of Stephen Squinted and, of course, the cosmic cliffs. Now, what are the cosmic cliffs, you ask? Well, the cosmic cliffs are a nebula, and the picture really showed the process of star formation. I will edit in the photos so you can still see them near their names, but for now, this is it. Anyways, these two were really nice images that served as really nice desktop wallpapers and show us a lot about star formation. But the photo that I'm interested in today comes from actually much closer. It's Jupiter, and of course it's the Europa, not the Europa League, Europa. So Europa is the moon of Jupiter, and what excites me is that we can, if at this distance we are able to see planets clearly, and even their moons at long distances, we might even be able to magnify this much and see planets correctly. And that's what makes me happy, because let me tell you, primer to finding various types of various types of exoplanets, including those habitable ones. But before that, let me give you a little bit of explanation into what is an exoplanet and how do you find one. Then we'll discuss how we can find habitable exoplanets and how James Webb Space Telescope is going to help. We might also discuss the possible risks and mistakes that might be made, and we will discuss how the future is looking bright. So without further ado, let's get started. So an exoplanet is simply a planet that belongs to outside, or exo, our solar system. This is a simple enough explanation, and well, it just belongs in the name. Planets, exo, or outside our solar system. If that's clear enough, let's now discuss how you can find these exoplanets. Note that any method, criteria, etc. that I will be introducing and talking about in this episode is going to be very rudimentary and massively oversimplified, but let's just assume for the sake of simplicity that these are correct, because there's tons of maths and science that is really involved with all of the process. So let's get started with that. So first of all, let's talk about the planetary shadows. So this is a star, this is a planet, but let's just zoom out a bit. See, this is your field of view. A single star will obviously look like this, and there will be many stars. So I'm just going to draw a little bit of cluster. Again, oversimplified very, very, very much, but this is a visual representation of how the star, there are many stars in the sky, very close together. Let's say I want to choose, alright, let's circle this one. So let me just magnify it. We've got our sun, which we can give a friendly name like Dan. So let's call this star Dan. So Dan looks like this. Dan, of course, is very bright and occupies an overwhelming majority of its stellar system. Here's a very, 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 very tiny star or something orbiting this star, which we will call a planetary shadow. So, what's exactly a planetary shadow? Well, basically, when there's a star and a planet is orbiting it, it leaves a bit of a shadow. A noticeable one, not a big one, and gives off a bit of a smudge. This is its planetary shadow. Now, this planetary shadow is more visible than ever thanks to JWST. So then this is not much magnifiable, but we can say for sure this might be some sort of exoplanet, perhaps. But there are, of course, false alarms. Why are there false alarms? Let me tell you. False alarms happen all the time. This is because this could be, I don't know, an asteroid, a really tiny star superimposed in a multi-star system, or even a comet. But however, it's generally a rule of thumb, because these things are often very small to actually make a noticeable shadow, that when you see this sort of small shadow or smudge, it's either some sort of spot, sunspot maybe, or it's a planetary shadow. Okay, great, you found an exoplanet, but you want to see whether it's habitable. These are the criteria that you need to establish. Here is a very bad visual representation, but assume this is a star. So the ones that orbit very close to it and have short orbits near the star, they're too hot, like Mercury's and Venus's. When you go a little here, you see planets that are too cold, receive too little sunlight, and they are, of course, not suitable for life. When you go in this sweet spot in the middle, you really see what is going on. This is the Earth, or Kepler 22b example. They are hot enough to receive enough sunlight to sustain vegetation, but not too close as to just burn the atmosphere and bombard them with radiation and just cause an unlivable mess. This is called the Goldilocks zone, after the famous fairy tale. However, there's more to this than just being too hot or too cold. How do we know for sure, though, the planet is in the Goldilocks zone? Well, there's a simple formula. It's not simple. It actually involves much more math, but if you come across a news story, for example, and you want to verify whether this exoplanet is going to be habitable or not, there are a few things to discuss. A bigger calendar means more distance. See, a longer year means some place is farther away. Why does this happen? Because distance. Simply put, a star or a planet takes more time to just circle around, even though it is fast, even though it's huge. The planet will still take a lot of time to really do that orbit across whatever star it has. Like, that is a given. And so let's say you have a planet that has a very short year. You can assume that planet, who is making very fast revolutions, has to be close to their star. While a planet, that means if a planet is moving and then coming at the same place you saw a few years ago, that means that it's going way, way, way too fast. If a planet is taking ages to move around, that might mean that the year is slow. This can even be, for example, some planets have 300-year long years, and so on and so forth. But when you get into the center of it all, you actually see a year that is roughly same to ours, which is around the range of 9 months to 5 to 6 years. If you see that interval happening in your exoplanet, you can assume that yes, this exoplanet might be in the Goldilocks zone. But that's no exception. For example, you can have gas giants in the Goldilocks zone, or Mars, which has no atmosphere. So how do you verify these? Well, there's another indicator of habitability. It's called bioscience, and it looks at the biological signs that a planet gives. This indicates things like an atmosphere, as well as things like how much oxygen is there. Is there H2O? And it looks basically at these biological components and decides whether it's habitable or not. However, this is not a reliable method. Firstly, finding which elements a planet has is hard. And even if you get to know, things like oxygen and hydrogen are actually relatively common in our universe. And even if a planet has water and oxygen, it may still not be able to harbor life. Like take Mars, for example. So it has oxygen, it has hydrogen, but it does not sustain life, and that is a problem. So you have to give more information to really understand if this planet is habitable. Coming in is the factor of size. So these are the planets. So here's, for example, you have very small planets who are too small and have little gravity. So let's take an example from our own cosmic backyard. Let's run back from all these exoplanets back into our solar system. We've got Mars. Now Mars has 2 moons. Mars is in roughly near the habitable zone. Mars is also like very suitable. Not suitable for life though, because of 2 things. First of all, it's got a very volatile atmosphere which is really thin and doesn't do much, and it causes a thing as cosmic radiation. This radiation is preventing it from having life. Years ago, it did have a proper atmosphere, and that may have harbored life, but we don't know for sure. But if I were looking from outside and I just took a hint and took a punt with its bioscience and all, I would say, this seems like a moderately habitable exoplanet to me. Not now though that we know and we've sent rockets there. And this becomes hard because we really don't have a lot to say. But let's say we discount small planets. What about big planets? Well, irrationally big planets have another problem. They are often gas giants. They are too big and too dense to have any surface. Everything becomes gas and just causes problems because there you can't have life. And when you take all these criteria into account, things like bioscience, Goldilocks zones, and size, which are now more easily accessible than ever with the James Webb Space Telescope, we still cannot tell if a planet is habitable or not. There's no guarantee. So, and even if it is habitable, there's no reason to assume it's inhabited. Maybe there's no species yet. And I'm not just talking about intelligent aliens. I'm talking microbes, I'm talking plants, I'm talking all sorts of life. And if they don't exist, it'll cause problems. And because if they eventually evolve and do exist, humans will be there. And this will cause massive problems in the long term. Even then, it's an optimistic future. Except for things called how time travels and time dilation. So first thing is how much time passes. So if you watch the movie Interstellar, you know that a second on Earth is about 7 years on Mars. A second on that planet they go to, Miller's planet, is 7 years on Earth, which is a big problem because time goes unevenly on various planets. This is a weird physics concept, but it's true. I mean, if I were, for example, to go on a planet, if I were to go on another planet, let's take the example of one of my cousins who is about 8 months old. Okay, and that planet has a different measure of time altogether, a different calendar altogether. I spend, let's say, a month there, and let's say every day is 2 years on Earth. I am 13 right now, and I go to that planet. I spend a month there. I come back a month older, you know. But then that person also my cousin though grew from 8 months to 2 year 8 months, and eventually he is now 30 years old, and this causes mind-boggling problems. When I was gone, he was a toddler. Now he's a middle-aged adult. I, meanwhile, have only grown 1 month. I'm still a teenager. And this is the sort of time dilation that is so-called theoretically possible, and this is really great for science fiction stories. So this type of time dilation can also happen when a lot of time is happening here, not there. A lot of time is happening there, but not here. But there's more. There's also the fact that time travels differently because of light. Well, light is extraordinarily fast. Let's say I shine a light from a planet that's light years away. Well, see, this is a telescope. Now, this telescope shot light here on Earth. And when this happened, I send this light here to Earth. Let's assume it traveled in a straight path, which obviously it didn't. The Earth is, because I was 1 year light year away, and light travels, a light year is basically a year by the speed of light. Well, when it reaches Earth, you know what? It's going to be a year has passed, and something else is happening on this planet. And the photos we are looking of are of thousands of light years before. For example, we think it's habitable, but we saw something that was thousands of light years away. Now, though, in the present time, it might be undergoing a hypernova, and so by the time we reach it, even if, okay, let's say this hypernova planet is 1,000, let's say a planet is 1,000 light years away, and we can travel at 1,000 times the speed of light, FTL, 1,000 FTL. It still causes problems, because even if I go there and if I get a signal from a planet that's 1,000 light years away and I reach there in 1 year, it's 1,001 years. Let me repeat that. 1,001 years that I'm outdated about. That is crazy. But you know what's even more crazy? The fact that all of this might be leading to something wonderful. And even with all these flaws, space travel remains a great alternative. So, I'm sure that James Webb will help us find a new Earth. It might be different than ours, but James Webb is a project of great magnitude, and the work it will do is going to be great as well. Well, for watching, thanks for watching, and I'll meet you in the next episode.